Okay, now let's try to work with only r equals to 1/2 and see what solution we get. Okay? So for r equals to 1/2, let's see what this becomes. This becomes, well, if you simplify this becomes a1 times 2r squared plus, I think you get 5r plus 3 minus 1, so it's 2 equals to 0. Okay.
Where did that come
From here. Just multiply everything and factor out the a1. Okay, so this is what you get if you factor out the a1 and just expand everything and simplify. And see, our choice was r equals to 1/2. You could also work out for r equals to -1, but it's almost the same thing, so we'll just work with one of them, not two. Okay. So for r equals to 1/2, we have this equation. Since r is 1/2, what is the value of this? I don't know, but I know that it's a positive number because everything is positive, right? If you plug in 1/2, it's positive. So the only way that this is equal to 0 should be
A1 is 0.
a1 is 0. See, this is non-zero. Non-zero times something has to equal to 0. What is a1?
0.
a1 must be 0. So that's the immediate outcome of the second one. It's not always that case, but somehow it happened that we found that a1 is equal to 0. Okay, so we have, so far we have the following fact: r must be either 1/2 or -1, and we chose r equals to 1/2 and we proceeded, and the immediate consequence was that a1 must be 0. That was what we got from the second one. Now this one, what is this? What is this called? I mean, we can solve this for the other an, right? We can let's see. Let's multiply this out and see what we get. See, r is 1/2. So this thing now becomes 2 times n plus 1/2 minus 1 is n minus 1/2. N plus 1/2 plus 3 times n plus 1/2 minus 1 times an, and if I move this to the other side, that's an minus 2. This is n squared minus 1/4, multiplying by 2, you get 2n squared minus 1/2. That's what you get from the first one. Plus 3n plus 3 over 2 minus 1. Okay? Times an equals to an minus 2. And let's see, these cancel, and you get 2n squared plus 3n times an, which if you solve for an, you get an equals to 1 over 2n squared plus 3n times an minus 2. For n, when does this happen? N
Equal
2 or greater than 2 or greater than 2. All right, what is this thing called? I mean, you can use this over and over again for n equals to 2, 3, 4, 5. Right? You use this over and over again, right? If you know that what a0 is, that will tell you what a3 is, right? For a2 is, if you set n is 2. If you set n equals to 3, if you know what a1 is, that will tell you what a3 is. So you can use this over and over again. What is that called?
Recurrence relation.
Recurrence relation. That's what it's called. Okay, that's called the recurrence relation. And it's good to have the recurrence relation because if you have it, then knowing the previous terms will tell you what the later terms are. Okay, so let's try to use the recurrence relation. We can erase everything. and write down what we know so far. We know that R equals to 1/2. A1 is 0. A0 is arbitrary. And we have AN equals to 1 over 2n squared plus 3n. AN minus 2. And sometimes it's easier to compute if you factor it by n. So that's what we have so far. Erase everything. Now we just have to plug in values and keep getting it. Okay. So A0 could be anything. A1 has to be 0. What's A2? A2, you can use this one for n equals to 2. So it's 1 over 2 times 2 times 7 times A0, right? So it's 1 over 14 A0. What's A3? It's 1 over 3 times 2 is 6. 6 plus 3 is 9 times A1. But what's A1?
0.
0. So A3 should be 0.
Every other one is going to be.
Yeah, so you can see that every odd term will be 0, right? Yeah. So every odd numbered ones will be 0 because A5 will be something times A3. A4 is 4 times 2 is 8. 8 plus 3 is 11. A2, right? So that's but A2 is 1 over 14 A0, so it's like 1 over 44 times 14 A0. Let's not even bother to multiply them. Yes?
So back to the general solution, the 2 terms and then the long one, the sigma. The first 2 are just used to find a solution so that you can find the recurrence relationship, correct?
I mean, you really need to work it out to see when you start having the recurrence relation. It's not always the case that you get the recurrence relation starting from 2.
But no, but I'm saying the ones that don't have the sigma are used to find what
the ones that do not have the sigma will give you
a solution
some conditions on the solution.
Okay.
Some conditions on the solution that gives you a separate thing. But once you start with the sigma, once every sigmas start manufacturing all these terms,
right,
then you will get the recurrence relation. Okay, A5 is
0.
something times A3, but A3 is 0, so it's 0. A6 is 1 over 6 times. 6 times 2 is 12. 12 plus 3 is 15. What's that? 390. That's 90. A4. So that's like 1 over 90 times 44 times 14. A0. And I'm getting tired. So let's just stop here. Okay. Usually on the exam I might say find the first non-zero, 4 non-zero terms or something like that. 5 non-zero. If it was 5, I would put, I need one more because A0 is non-zero, A2 is non-zero, A4 is non-zero, A6 is non-zero. So if I stop here, I'll have 4 non-zero terms. If the question is asking for 5 non-zero, you will have to do one more. Okay? All right. Anyways, if you put them all back into this form, what's the answer now? Answer is that the solution looks like y equal to x to the 1/2 power. Just think about x to the r in front, times a0, which is just a0, we don't know, plus a1 is 0, so that disappears. 1 over 14 a0 x to the what power? Second power, right? This is really a2, right? a2x squared. Okay, a3 is 0. a4 is the next non-zero one, which is 1 over 44 times 14 a0 x to what power? 4th power, plus A5 is 0, so that the fifth power doesn't appear. A6 is 1 over 90 times 44 times 14. A0, x to the sixth power, plus, and then it never ends. Okay. So we found the solution of that differential equation, which is this one. And once you see the solution, you see why we really needed the Frobenius method for this equation. Because if you just started with y equals to a n x to the n without this plus r, there's no way you're going to get this solution because of this fractional one, right? So you see that there's a definite need for Frobenius method for this differential equation. Okay. Now let's talk about why this differential equation is so different from the other ones. Okay, so we'll go over and talk about singularity.